Let's go live here. Let's get in there. Okay. Give it a minute to get going. I think it says 2 concurrent viewers. Not sure why it does that, but all right. So, welcome. Welcome. Hello, hello, hello. It's upstream. Hello and welcome back. Now, we have some problems to go over. Let's do this. Yeah, man. All right, let's get ready. Just hop right into it. So, welcome. And today, I think I already went over this problem the other day. Explain how this works. This is a breadth first search algorithm. Rather simple. You just have a set of things. First thing we do is parse what we're looking at into an adjacency map. Each spot has a certain number of has sort of positions next to it that it can go to, so to speak. You can move from one empty space to the next, so you can associate with that empty space the empty spaces around it. So that's this generate adjacency map. And actually, this is the reducer that performs that, and then the actual function call. And then what we did was we performed a breadth first search over the adjacency map, and we just said starting from M, and if we ending at C, basically we would sort of traverse each node that's in the set, starting with M. We would accumulate the other the nodes that can be reached. We would also push into the set, and we would perform this repeatedly until either A, the 2 sets when you compare them are equal, right? The previous set and the next set, or the current set after you've calculated and the previous set. If they're equal, then that means you're not able to get any more elements, and you're done. Or if you have C in that set, that means you were able to find a root that retrieves what we're looking for. Now, this is maybe not the best algorithm possible for something like this, but it works for these test cases, and it works in general as well. It's just not the most efficient, possibly. All right, let's look at 118. So this is just some what do they call that? Clojure code that does each of these pieces. They're sort of broken up into pieces. I'm not going to go through all that, but yeah. You just iterate over that breadth first search, and drop while those 2 conditions don't hold, and then grab and then finally check if the thing you stopped at, if it has C in it, then return true. If it doesn't have C in it, then this will return false. Okay, so 118 we want to go to now. Let's take a look. Re-implement map. So here's the deal. I clicked this button the other day, and it messed up my OBS. So OBS has all kinds of, we'll call them quirks. One of them being you can actually click this button, and then suddenly the display here, whatever that's called, it records my desktop display. So that display suddenly doesn't function, which is great because that happened yesterday, and I was about an hour and a half into the stream. That happens, and then I had another hour and a half where I was talking and nothing was shown on the screen, which is great. It's pretty funny. So next is map, and the idea behind map is you basically build a lazy sequence of you visit each value in a certain collection, apply this function to it, and return a lazy sequence of that application, which is basically give you all those values in that collection with that function applied to it, each one with the function applied to it. So that's effectively what we did. A lazy sequence, if it's empty, return an empty set. That's the base case, and then the iterating case or recursive case, we say cons f of what's the first thing in the collection, and then recurse on map2 with the rest of the collection, and then keep passing this function f. Real simple as it turns out. Not too many moving parts there. 119. I'm not going to say easy anymore, but I can say simple. So winning at tic-tac-toe, this is an interesting question as well. I think I went over this yesterday in detail, but I was kind of disappointed, like I said, because I couldn't I couldn't, the video that ended up getting uploaded doesn't really have like an explanation of this. This was really cool. So basically you have a tic-tac-toe board with O's and X's and E's for empty spots, and I won't even read this part, I'll just describe it. So if you remember tic-tac-toe, you got to get 3 in a row in either horizontal, vertical, or diagonal. So there's a way, so what they're asking for is not just if someone won or who won, but they want to know where can you place where can you place the piece that they give you, which is in this case would be X. Where can you place that to create a winning position? And then in some cases you can't. And so real simple, I just evaluated, okay, if you put X at any empty spot, you get a new board state, and just evaluate the board state and then filter over the positions where you win. And so the beauty of this algorithm really comes from actually the winning function. There's a function to win that's kind of involved. It's really cool. And then there's also what I did is, okay, after I have a function that's reasonable for winning, then you just update. Yeah, so for every position, if the piece at that position is empty, then we're going to check. We're going to calculate the winning, whether or not you're a winner, based on this update, which is oh yeah, actually it's a little bit involved here. It actually, yeah. Actually, this will iterate over. This will check every board state, and the only thing is it'll just return the same board state over and over. If it's an empty spot, this actually might even be incorrect, technically incorrect. It's not incorrect. It's only incorrect if the board state you're looking at you've already won. In which case, we assume that case isn't going to be given to us because it doesn't really make sense to try to win if you've already won. But yeah, so this only operates on the in theory only operates on the empty spots. What it actually does is it tries every spot, and it only will replace an empty spot with what you're looking at, or with the piece that you want, and then it will filter on whether or not that's a winner, the resulting board state. Yeah, there is a way to actually even make this more concise, and also make this more concise as well. There's even better approach than this, but I like this. And yeah, the idea is you can find the columns relatively easily using this function of the board. Then you can concatenate the columns with the board, which is the rows, with a diagonal, forward diagonal, backward diagonal, which you can say just get in on the board. You map over this range twice, and it doesn't have to be this range twice. You could actually have used just like a different function here, a different approach, but could have just mapped over one, and then in this case, take the size of the board minus this value. In this case it'd be the size of the board minus this parameter, and then this would be just the same parameter twice, right? So you can concatenate, and then what you do is and then again, this could even be made more concise as well. Like I mapped everything to a set, filtered on the sets that only have one element in them, and then concatenated all of that, all of those sets. Yeah, apply concatenate. So what you end up with is a sequence of sets of size 1, and so you want to concatenate all those sequences. So you apply that single sequence that contains that sequence of sets. You want to concatenate those as parameters to concatenate, right? And then you take the first one of those that has an X or a 0, and if none of them, if there's no winner, then obviously you didn't win. Better than that, you can just do a sum of, don't even apply either of these three. You can just do sum is either XXX or not even sum. You do is it sum? Yeah, it's sum. You do XXX000, and instead of a hash set, use a hash map, and the hash map will map to X or O depending on which one you've got. And it's way more efficient than doing all this. It's efficient in a lot of different senses. Like it's more terse and sort of more efficient here. Anyway, so not to spend too much time on this, but I looked at that yesterday, and I think this is one of the things that we didn't get to really. You couldn't really see it while I was talking about, which is pretty unfortunate. All right, next. 120. See that? Sum of square of digits. All right, this is interesting. This also can be done a lot more concisely, but more breviloquently. But I wanted to use this sort of maths approach. Another approach is just convert it to a string and then convert each of those characters into their respective digits. Map the characters to their digits. I'm not sure which one's more efficient. I think it's pretty efficient to actually convert it to a string and then convert it and then map the characters. But yeah, you could do it that way. You could do it this way as well, and then you just calculate the digit square sum. And this problem is interesting because, like, there's a few things that are interesting about it. Like, one thing is, technically, this kind of caps out at 50 after 100. So if you were given an infinite set, as long as it contains 100 as a subset, then it'll just be 50. In fact, you only need to consider of any set the first 100 elements for this question. So you can actually take infinite sequences and process them reasonably here. Even though that's true, this doesn't sort of automatically. You kind of have to figure that logic out to handle that. Lazy sequence, like, I don't know how to express it. I kind of want to say, like, functional programming, in theory, you could determine whether or not you'll have an infinite sequence, infinite loop, or you won't be able to terminate on an infinite sequence. But in some cases, you can determine whether or not you'll terminate. I don't know. I don't really know, because you don't really have notions of infinite sequences in other paradigms, like in although, because in functional programming, everything is sort of abstract, so you can do some pretty wild stuff that you can't do. Not that you can't do in other languages, but it's very. I guess it's just unusual. Excuse me. Yeah. Anyway, pretty cool. So that's 120. I'll go through that briefly, but really simple thing. 121. Universal computation engine. This was kind of neat. There was also a very concise solution to this too that someone gave. I realized that things being breviloquent really has a lot to do with. Let me look up synonyms. Not definition. brusque, terse, compact, compendious, sententious, succinct. It's compendious. Not a very succinct word, compendious. Sententious. Aphoristic. Aphoristic and sententious. Some good words, man. Compendious, containing or presenting the essential facts of something in a comprehensive but concise way. Yeah, compendious. Sententious. Moralizing in a pompous or affected manner. Sententious rhetoric. Interesting. Let's not be sententious here. Not sure what that has to do with being compendious. Aphoristic. Aphorisms. A pithy observation that contains a general truth, such as if it ain't broke, don't fix it. Aphoristic. The aphoristic of the day. The mimetic aphoristic of the day. No. Sententious. Yeah, let's not be. So sententious isn't what we're looking for, but compendious. Brief. Compendious. Succinct. Short. Summarized. Synoptic. Brief. I'll be brief. Synoptic. Of forming a general summary or synopsis. Interesting. Eloquent. Oh, synoptic. Compendious. Right, so there's a more compendious. I've noticed about if you're looking to write a more compendious version of something that you're looking to solve, you could design it well in the first place. Like in other words, you could in your mind you can think of something that's succinct and write that initially. Though what I've learned is the tendency is to first solve it and then you can make out pieces that can be optimized and sort of optimized in fewer semantic pieces. So as an example, you can see this portion here. This has a relatively, let's say, ordered structure to it. And you could actually turn this into a map where you say, look, if the opcode maps to each of these values, then you're going to return this function with this particular sort of value. And what you could do instead is actually just return this with a map that maps from here to here, and then evaluate that map here. Because these are actually functions, right? So you can actually return these functions. You return the correct function depending on what the opcode, the operation symbol is. So you could actually make this more concise by, you could sort of reduce this by a few lines. And also you can reduce these different cases as well. Don't recall exactly. I'm not sure I was just hearing. You could yeah, you can handle these different cases as well. How to do that? Oh, excuse me. I actually don't remember. But Yeah, it's pretty simple. This question, after all, it's just a matter of sort of recursively operating on the expression, and yeah, and when if you see a sequence of things, then you take the first. If you take if there's a few different cases where you could say it's badly formatted the expression, but you suppose that there's at least one element, and in addition to an operation, so it's got to be great. I actually went with at least two expressions because a lot of these operators have. Didn't matter in these cases, and it's kind of ambiguous one way or the other which one it should be. These operators often can operate with a single parameter in addition to the function, but they tend to default to like a kind of what do they call that case? A degenerate case. So it's kind of like, you can exclude the degenerate case or keep it. It doesn't really make a difference, I think. And you say, and actually I probably don't even need this. I probably could do without this altogether. That means do without these. This, on the other hand, you do kind of want yeah. It'll throw an exception, I think, if you don't throw this. Excuse me, which I guess is fine. Don't necessarily need to use a condition. You could use a hash map. But yeah, this would just be, I don't know, one way or the other. If you didn't use a condition and used a hash map instead, you would just you get like nil, which would throw an exception. So you probably do want like a default value, something like that. If you these parts, I kind of didn't know what to do, or not that I didn't know, but yeah, this is so. If you're looking at something that's a sequence of things, then it's got to have some operation, and then you can recursively determine the expressions for the rest of the operations, the rest of the expressions. So recursively evaluate the expressions and then evaluate everything with respect to the operation that it's given. And if it's not a sequence, then you're looking at either a number, which you just return, or a variable, in which case you want to check if you can find this expression in the variable map, in which case you return whatever it's mapped to, that number. And if it's not a number or a variable, then you assume it's something else that doesn't belong there, and say it's badly formatted. Simple explanation of what my code does. Now, what does the code for other folks do? Oh, I see what that noise was. I got this paper over there that my mouse is scraping against. Now, some other folks had, now this solution, this example, this is what I was talking about, uses this ops op map. These bindings, this is a function, you'll get the bindings. Anonymous function, partial, right, you call this with the bindings. Yeah, you can what is oh yeah, this gets pushed into the partial, gotcha, which, right, this returns a function that'll take, so the ops in the form will be bound to this, with this function, this is what it returns, it returns this function, but with this option, the operations in the form bound to it, and then the function will take bindings. I thought this was kind of clever how I did this. I didn't do it that way at all. I just returned this function which takes a map. And then what he did, he also had get bindings of form. This was kind of interesting here. If it's sequential, then do this. If it's not, then do, now this get bindings of form, that really threw me off. But what happens is this is actually a default value. If the get bindings fails, then you return this value. Yeah, it's super confusing, but that's what happens. And this will actually not handle the edge cases that, like, when if you put garbage in there, it won't handle it doing it this way. This just assumes that everything's nicely formatted. So if it's sequential, you'll get, this what I was describing, right? This can be greatly simplified. And then if it's not sequential, we just assume it's just, you just return whatever it is. Oh yeah, you get it right. So this is kind of clever because it does handle, like, if you give it an expression, if you give it like a constant, the constant won't be in your variable map, so you can just return that directly as the default. So that was kind of a clever way to combine these two. But obviously there's no badly formatted checking, there's no bad formatting checks to be found. So this would sort of be assuming that you've already checked that the format of this expression is correct, which that's actually like sort of lexical analysis, which I've actually worked on that at university. I did help build like a compiler, and there's a bunch of different parts to compiling. But that's one thing you do, is check that the thing is sort of formed correctly in the first place when you parse it, which is kind of neat. It's funny, I'm reflecting on it now that I'm much older and more experienced with software. It's like, it's actually very easy in some sense to write a, I don't want to say it's easy to write a compiler, but it's sort of easy, not actually, I shouldn't say it's easy. I've become so much more familiar with like parsing and what do you call that? Parsing and sort of evaluating, that it's like it's just a few algorithms realistically to take the text that you're looking at and create a program structure, a abstract syntax tree is what it's called. But basically, yeah, to kind of gather the data of the program together into a data structure. It's actually not too terrible after all. Something like that. It's actually not, like, it is somewhat simple. It's kind of a simple thing. It's not unbelievably, I guess, complicated. It is rather complicated though, after all. What's interesting though is all the different kinds of optimizations that are made, that are done once you've got a working compiler, what you can do, the different kinds of things that can be optimized. That's really cool. I appreciate that a lot. Yeah, I was just talking with a coworker today about what volatile does in your code. If you're dealing with C++, you throw volatile in there on your that keyword onto one of your variables as an example. You'll see, and then you run it through a something like Godbolt, which shows you your code compiles to in assembly. So it compiles to assembly code, and it'll show you what that code is, Godbolt. And what's cool about that is you can, what was I saying? You can, yeah, compile your code to assembly. Godbolt will show you that assembly code. And what was I saying? What was I getting at? Oh, we were saying, yeah, what's really interesting is that if you put volatile in there and throw it through, push it through Godbolt and look at the assembly code, what volatile does is it actually turns off some of the optimizations to make sure that the memory is constantly looked at. Every time you reference the variable, it'll actually, instead of caching the variable somewhere in a register, it'll actually force the program. It'll keep all the register lookups. It'll force the program to go back and forth from the register to check and see if that variable changed. One of the things that happens when you add the volatile keyword. So it actually de-optimizes your code, which is pretty wild. I forgot why I brought that up, but I don't know. I was thinking about, I guess because we're talking about compilers, maybe it reminded me of that. It's pretty cool. But yeah, there's tons of optimizations. There's so much really cool stuff that your program can do, and your compilers do to optimize. In some cases, you actually don't want to optimize because it could cause your program to be incorrect. Volatile. It's like you could say it makes your variable magic. The variable is being it's basically magic. It's being tinkered with in such a way that it you don't know what the value of it is. You gotta constantly check up on it. Your compiler doesn't know, and nobody knows. Nobody knows. So, right, I babbling on over here. Let me. Yeah. So this could be made way more concise, but it's at the cost of these sort of formatting exceptions being visible. Alternatively, you can just throw an exception. I mean, that works too. Although exceptions are kind of tricky. I much prefer like catching an exception and writing something to a log. I like that. That's pretty good, generally speaking. So, that is 122. Okay, 121. No, 122. Get a little closer to new stuff. Well, not new things, but things that I haven't looked at yet. So this is pretty simple. Just converting a binary number to a string. There's at least 3 different ways to do this. One is sort of directly, and I'll show you how I did that. Another is, I call it direct, but I'll explain what I mean by that. Another approach is to use a sort of built-in function that interprets your string, reads an integer from the string, but interprets the string as a binary string, as a binary integer, as the binary form of an integer, as a base 2 integer, that's in string form. You can do that. That exists. I'll show you some solutions that use that. You could also 2R, where you'll see it means radix. So radix typically means the base. It's kind of equivalent term for base. So you can have the radix is 2, right? Parse an integer with a radix of 2. There is also the next one, which is another way of just parsing an integer with a radix of 2. There's 2 different ways to do that, you'll see. And finally, you could evaluate this from the sequence from left to right. Oh, wait a minute. Yes, you evaluate the sequence from left to right, and what you're going to do is when you see a value, you add, if it's 0, you add whatever it is, you bit shift what you've got to the left, and then you add that value to your integer, right? And you repeat that for each of these bits, and that'll also give you the correct integer. And I'll show you. So yeah, so I already ran the test cases. So what it does is, from left to right, you're going to take your whatever you've got currently, bit shift it to the left 1. Notice I used this, so that way we would end up right in the middle. Bit shift to the left 1, and then add. You're going to take your character. This is going to be a reduction over the input. So effectively turn the input into a sequence and operate over that sequence. So it'll move character by character. And because it's a character, you can just use a map, hard-coded map from 0 character to 0, 1 character to 1. There's also another way to do this part, which is subtract from the character, interpret the character as an integer, and then subtract from it where the integer, like the ASCII value of 0, whatever that would be. So 0 minus 0 would give you 0, and then 1 minus whatever 0 is would actually give you 1, because 1 succeeds the ASCII value of 0 by 1 exactly 1. So the next one. And yeah, so you can reduce over it with this function, right, character by character, and do exactly that, starting from 0, just bit shift to the left once, and then add either whatever that character converts to an integer. And also the other solutions, I'll show you those as well. So it's kind of a somewhat trivial thing. It's simple enough. So you could. It's kind of interesting actually. This fellow read in the string as integers anyway, which you don't really need to do. This is what I was describing, where you use 2 radix, string of 2 radix, and then read the string, right? Also parsing the integer with the 2, base 2. These are like the 2 different approaches. These are sort of like built-ins, taking advantage of this. Oh, I'm sorry, no. This actually will concatenate 2R, and then when you read string, I think the read string will process this as radix of 2 radix, or radix 2, base 2. So yeah, this is a read string built in, this parse built in. Both of these are just built-ins that do what I was describing. Otherwise, the way you would do it without using these built-ins is exactly one of these, or what I wrote, or this fellow did here. Yeah, you see, oh, no. Interesting, used a map index of the reverse. Anyway, you get the idea. Yeah, here the fellow subtracted as it described, converts both things to integers, subtracts integer of 0 from either it's a 0 or 1, the character. Yeah, you get the idea. It's kind of cool. Kind of a neat. It's such a simple thing, but there's enough variation to make it kind of an interesting question to look at, even though it's, like I said, super simple. All right, 123 doesn't seem to have anything. All right, so 123 is where we're at right now. So let's go ahead and run these. All right, reversey. So finally, it took a while to explain all of that. Just checking to make sure we're still, I guess, showing what we're doing. All right, so this is kind of involved, and I didn't finish it when I started working on it. And I will explain the problem. And then I guess, yeah, I'll code up the solution that I had, that I was working on. Almost finished it. I was really close to finishing it. So yeah, so okay, let's begin by just setting up the scaffolding here. the boilerplate here. Reversi, and we're going to take a board and a piece. They want to know the winning moves. We really should use color, I think. Yeah, I kind of prefer color, piece, or even player is better. Yeah, I'm not really sure. I kind of want to just use piece. I like piece better. White piece, black piece. All these piece. Let's go ahead and copy each of these. So we'll start with a let because this is going to have a bunch of functions. And what we want to do is I'll explain what we're even doing first. So let's start with the problem statement. Reversi is normally played on an 8x8 board. In this problem, a 4x4 board is represented as a two-dimensional vector with black, white, and empty pieces represented by B, W, and E, respectively. Create a function that accepts a game board and color as arguments and returns a map of legal moves for that color. Each key should be the coordinates of a legal move and its value a set of the coordinates of the pieces flipped by that move. Board coordinates should be as in calls to get in. For example, 0, 1 is topmost row, second column from left. All right, so I'll explain what's going on here. In order to really understand what's happening here, we got to go ahead and look at the wiki. We got to go ahead and look at the wiki. So, it's a strategy board game for 2 players, 8x8 uncheckered board. There's an original version, there's a modern version, I believe is typically called, is usually marketed and recognized as Othello. So there's actually a fellow that would watch my streams way back when whose name was Othello, and I didn't know who he was or what his deal was. I actually just thought he had an interesting name. Turns out Othello itself has a pretty interesting background. It seems to have something to do with the Shakespearean play Othello, the Moor of Venice, which is quite an interesting story in and of itself. But that's the reference to the black and white and the green, or at least it's suggested in this Wikipedia that has something to do with the story itself. Othello's story. So how it works is you have these. You start here like this in this board state, and then you say, okay, I can make a move. So one of the players starts, right? So I think it says the dark player moves first. So the black player makes the first move, and he picks. Basically, what you're going to do is you add pieces to the board, right? So he can add a piece in 1, 2, 4 different spots. They show it here where he can add the pieces. What's required to add a new piece is that there needs to be an opponent's piece between the piece you're going to add and one of your pieces, right? So you see how there's always an opponent's piece between, right? And you can do diagonals too, right? So there could be a white piece here and a black, and you could put another black piece there. And that's the basic idea, is that you just have to basically make sure that wherever you put the next piece, you can draw a line either horizontally, vertically, or diagonally between one of your pieces and the piece you're looking to put down. And it has to be on the board, right? Obviously. And all the pieces that are between the piece you're putting down and one of your already present pieces, all the pieces between those two that are your opponent's pieces become flipped to your color when you put the piece down. So they show that here, right? So they say, okay, starting from here, you have these 4 spots, and then you could go up to the top here, and if you do that, you end up in this board state. And then for the white move, you can go into these 3 positions. And so it's a very interesting game. It's constrained, but there's a lot of different decisions that can be made, a lot of different possibilities. Pretty cool. Programs can play it reasonably well, right? So if you go here for the white move, then you have these 3 white ones and 3 black ones. And then there are some cases. So I think one of the rules also for Othello is if one player can't make a move, then the other player gets to move. If neither player can move, then the game ends. And there are some cases where the game just ends early, even though technically the grid is not completely filled. Here's a case, right? No player can move. Neither player can move in these cases. This is, I guess, is another case. So it is possible to not fill the grid completely. And the game ends. And obviously when the game ends, whoever has the most of the board wins the game. Yeah. It is a game of attrition, I suppose. Something of a game of attrition. I don't think it's actually a game of attrition. I don't know what it is. It's a different kind of game. But it's definitely a very interesting game. And it was popular. Was a commercial success. Has professional, sort of a professional, not a professional scene, but a what do they call that? Competitive scene, I guess. That's a cool game. It's interesting. That's what Reversi is, what they're talking about, because I had no idea what they were talking about. So Othello, or alternatively called Othello. So it's pretty cool. What they're asking for is they want to know, given some board state and given some, basically which player is which move, which player. You want to know, you want to figure out what all the possible moves are for that player in this board state, and create a map of, okay, here's the position that you can go to, and then at that position hash to it the set of, oh sorry, I take that back. What you want is from, oh wait a minute, I think I misunderstood. So yeah, so you have, oh no, wait, 1, 2, 3, 4. 1, 3, 1, 0, 1, 2, 3. 1, 3, and then what is this? 1, 2 from here. Oh, yeah, I'm sorry, I take it back. So what they want to know is, what are the possible moves that this player can move to, and when they move, which pieces are going to be flipped of your opponent, right? So if you go to 1, so 0, 1, 1, 0, 1, 2, 3. If you go to 1, 3, this piece at 1, 2 gets flipped, right? If you go to 0, 2, 0, 1, 0, 1, 2, here, then this gets flipped, which should be 1, 2, right? And then if you go 3, 0, 1, 2, 3, 1 here for the white piece, then it should be 2-1 that gets flipped. And then also, finally, this one I think is 2-0, right? Yeah, 0, 1, 2, 2-0. This 2-1 is flipped, right? So that's what they're after. They're after this hash set of what are the possible moves for white, and then what are the consequent black pieces that are flipped, or for a given a player, find all of the possible moves, and then for each move hash use that move as a key, and then the value that that key is hashed to, or the value that's hashed to that key, hashed with that key in the hash map, is going to be a set of all of the opponent pieces, positions of the opponent pieces that'll be flipped. Yeah, pretty interesting game, pretty interesting question, and yeah, you can only move depending on what your opponent's board state looks like. So there's a certain interdependence that makes this a very, very interesting game. Also, one of the reasons I think why it was such a success. So how are we going to code this up? Well, I decided to break it up into pieces, but like I said, the simplest way is first you start with like a solution, right? And then you can code it up. You want to have like a solution. You want to break it into pieces, code each of those pieces, and then once you've got a solution, then you can sort of look for things that sort of make it, more succinct, or summarizes it better. Not summarizes, but makes it, I don't say more synoptic, but makes it more compendious. More compendious and brief. You can look for ways to do that once you've already got the idea. Once you've already got the idea in your mind, then code, break it down into pieces, and then you can go step by step. So, what do we do? Also, I really kind of want to use the bathroom. Kind of want to do that sooner than later. Also, let me take a break, but you could kind of ponder how you might solve this. I'll describe how I intend to solve it. So what I intend to do is loop over all of the, first filter over the entire board for things that are white, right? I can get the white, or whatever that the piece is. I can get the piece of interest, right? Get that sequence of those sort of board values. Then what I'm going to do is iterate over for each of those board values. I'm going to take one of the 8 directions that you can consider, right? Also have something to calculate and return that sequence of directions. And then I'm going to have a routine which from this position and a direction will calculate if there is, first off, if there is a move that can be made in that direction, and if there is one, it'll gather all of the it'll create a sequence of, or a set rather, it'll create a set of the values that'll be have to be flipped. And then what's going to happen is we're going to perform this for each of these pieces, and we're going to concatenate all of those results, right, for each position. So we're going to map and then concatenate. So map to each, so filter on these things, then process this sequence by mapping this function on each of those to calculate, to get a this key set pair, we'll call it. And then you can actually, then you can, I guess what we can do is just concatenate each of those key, each of the key set pairs, we'll call them, concatenate all of those results, or using like a mapcat. And then once that's all done, all that processing, we can push all of that into a hash map, and the pairs will automatically become a key value pair, the way the hash maps are implemented. And then we return it, and then we're done. That's it. Real simple sequence of steps to do here to perform. Let me go ahead and go use the bathroom. So I'll be right back. I will be back. I will be back. Put this here. Put this guy away. Say we're taking a break. Oh, we're using the bathroom really, so we're doing. And we'll just put everything away. Oh, one more thing. Okay, I'll be back. All right. Believe we're back. Believe we're ready to go. Can put my video capture back on here. Wrong one. Okay. So we're back. Welcome. Welcome. Okay. So reversey, pretty interesting question. Let's look to code it up now. So the first thing I want to do is get the set some sort of constants. So an empty piece is this guy. Something of a constant. No. Right? And then we want to say number of rows is going to be the count of the board. Number of columns is going to be the count of first of the board. And we'll just say if 0 of the number of rows, right? Because we could have a, this could be, I think actually doesn't matter, right? Because if the board is null, if there's nothing in the board, then it doesn't matter. We don't need to do that. Because if this is empty, then this will be empty. And count of nil, I think is count of nil. I think just gives you 0, so it doesn't matter. Also, first of nil, I think also gives you nil. Let's actually check that right now. First of nil, count of nil. There you go, done. What we can do is now we want directions. It's going to be for, we're going to do a list comprehension. And we're going to say I in range of number of rows, J in the range of the number of columns. And we're going to say when not equals I, J, and 0. And then we'll say return IJ. And I did this wrong. This is going to be range of -1 to number of rows. And no, that's not right either. No. It's -1 to 2. Right? That list comprehension gives us the different directions. And now we want flippable pieces based off of, we want the other target piece, we'll call it, which is going to be a map that we apply piece to, where we say if we have a white, then we want black as the target. If the black is the target, if the black is the piece we're working with, then white will be the target piece. So we can use the map as a function here, which is kind of cool. Neat thing you can do in Clojure. So we have our target piece, we got our directions, we got number of rows, number of columns, all these nice constants that we can make reference to later. And our flippable pieces, this function will consist of, it's going to be a loop we're going to use, and we're going to use an if statement for the base case, and then recur otherwise. Actually, we want not just an if statement, but we want a condition, a bunch of different cases to recur on. And what we're going to take with our flippable pieces is we're going to take, we have the board. We've got this RC, which is going to be the, the board is in scope here. We don't need to put that here. We want RC is the row column, the sequence of row column values, two tuple of 2 values. Now we want the direction, also tuple. And we want one more function here called inbound. Inbound. And that'll take RC. And we say, you could do RC like this, I think is better. And we just want every true of greater than or equal to the R is greater than or equal to 0, C is greater than or equal to 0, R is less than number of rows, C is less than number of columns, and that'll give us whether or not we are inbound. And RC direction, I think that's all we really need. Yeah, everything else is sort of in the contextually there already. So we're gonna say, so we start our loop with, now we have RC, we'll map to remap RC to row column to a map of, now this is kind of interesting. This will take, RC to the map, RC to direction. So this is a XY, is sort of a, this gives you like a vector, in a unit vector in a direction. It's kind of like a unit vector, not quite a unit vector. Something like a unit vector. And this gives you the two-dimensional coordinates. And mapping will actually take, you actually want to do, you'll get two arguments to this plus sign, one from here, one from there. And so this will actually give you the sum of each, sort of zipped, which is, it's kind of cool how that works. It's kind of neat. Then we have this ag, which would initially be empty, and then finally we want previous to be, we'll keep that as nil, or you don't really need previous, actually. Take that back. So you have, this is going to give us the flippable pieces as well as the spot we end up, the position, the new position that we can put a piece down to. So if we are not in bounds, right? If not in bound, and this is going to take RC. Right, we'll spread out RC. If we're not in bound, then we want to return, and we're going to return the move, nil, and the set, empty set. Right, failed case here. If we are in bound, then we want to get in on the board and check that RC, get this piece, this value, and check, is this equal to the target piece? Right, is this equal to something that we want to jump over? If it is, then we can recur with RC mapped. Yeah, calculate this again here, and then conj the ag with the RC that we just looked at. Right? If this is an empty piece, so now we're recurring. If we end up at an empty piece, that means we've got a valid position, a valid move. We want RC, and we want this set ag to return these. So we keep recursing in this case, right? We keep jumping over pieces. If we find an empty spot, then we want to return this. If we end up out of bounds, we return this. And then finally, if we're basically, if we find something that's not, if it's not the target piece, I mean, there's really only there's only one other case here, which is it's not the target piece, it's not an empty piece, it's the and we're in bounds, it's going to be the same piece, which we can't jump over that. It's got to be only, I think, that's something we can check, if it's only opponent pieces. That's actually a good question. In such a position that there exists at least one straight, horizontal, vertical, or diagonal occupied line between the new piece and another dark piece, with one or more contiguous light pieces between them. Okay, so I think I think the light pieces need to be contiguous. We're going to ask that question. Othello rules contiguous. That's actually a good question to ask. I want to know. Can you show me? Computer version of Othello is in the Windows operating system. Cool. I didn't know that. It's pretty neat. It's pretty neat. Contiguous contact details. Two differences. Okay. Each piece played must be laid adjacent to an opponent's piece so that the opponent's piece or a row of opponent's pieces is flanked by the new piece and another piece of the player's color. All of the opponent's pieces between these two pieces are captured, turned over. It can happen that a piece is played so that pieces or rows of pieces in more than one direction are trapped between the new piece played and other pieces of the same color. In this case, all the pieces in all viable directions are turned over. A piece is played so that pieces or rows of pieces in more than one direction are trapped between the new piece played and other pieces of the same color. Okay. Between the new piece played and other pieces of the same color. All the pieces in all viable directions are turned over. Oh, now this is interesting. My algorithm is wrong, actually. My idea is incorrect. It's the other way around. Oh, that's very interesting. Oh, wow. So basically, you can move to a... No. My algorithm isn't done yet. So I do have to take into consideration that there could be multiple directions. So actually, you can arrive at a position in multiple ways, in which case there'd be multiple directions to consider. Oh, excuse me, I didn't think of that. So actually, I need to map this correctly. So when I push all these values into my eventual hash map, what I've got to do is actually update the keys rather than just in place the keys. This is going to be interesting. Okay. I'll show you that. I'll show you that, taking the union of these sets. So anyway, if we're not inbound, return nothing. Otherwise, yeah. So otherwise, we're going to return that we bumped into the piece of the same color, and we can't actually get something in the direction that we're looking for. I think that's ultimately what we get. Yeah, I think that we can. That was the ruling I was looking for. If there's like black, white, white, black in a row, then we would assume that we can't place like another black after the second black, something like that. Yeah, yeah. Like if you have something that looks like this, like B, white, white, B, we would just say that you can't put another black one here to get these white ones. You would need to have a white one here, and then you could put a black here, and you would just get this one. Yeah, I think that's true. Anyway, so that gives you your flippable pieces, given a direction and a row column position. And what we want to do is say, let's get a function that returns start or possible positions. Which will just be filter in a moment on a 4. We'll use another list comprehension. We want to say R, range of number of rows, C, range of number of columns, and then we want to say RC, and we filter on if get in board of RC is equal to the, what do you want to call this? Piece is equal to the piece. So yeah, so filter on those possible positions, right? And then what we're going to want to do is actually evaluate over these possible positions. So we would say, sort of for each, I guess it'd be sort of for each, we're going to, I said we map cat, right? That's what we're going to do. So we map onto flippable pieces. No. map onto possible positions. This function, which is flippable pieces, and we end up returning a whole bunch of things, right? We map cat. What we want to do is reduce over all of these possibilities, and we'll say, oh, first things first, we want to remove, yeah, we can filter out if the first of this thing is equal to nil, right? That's what we want to start with. So we only want the ones that are not nil, right? Do that first. And so what we end up with is this. I can use a threading macro here as well. Okay. Right. Let's just take a space. And then filter as described. Okay. And now we want to perform an update. We want to perform a reduction, I think. It's going to be reduce over this hash map and use this function, which is going to have ret and key value, rather a sequence of these things. Sorry, no, this is concatenated. Yeah, so this is key value. And what we want to do is we want to update in ret. We're going to say the key, and the value is going to be into whatever is already there. It's a function. Takes whatever's there, push into that from V. I don't think it works like that. If we update in, what do we get? What happens if we update in? What if the key, if there's nothing there at that key? Or just update, I guess. M key F of X. Key is a key, and F is a function that will take the old value and any supplied arguments, return the new value. The key does not exist, nil is passed as the old value. Okay. And we'll say if it's nil, we want to make it a set. I mean, we can just say get K from ret, or yeah, I mean, okay, fine. Now we do want to push into this though. I want to associate. Fine, I guess. No. This is confusing. Get rid of K, otherwise it's just an empty set. And then we'll push into from V into that. That'll be the function we call on yeah, that's fine. Seems kind of redundant. But that's the reduction we end up doing. And I don't know what this is going to look like. Reversey. Let's go. See that in action. Okay. Oh, no. All right. Line run. Let's go. Okay. So, let's see what happens here. R in this context. Where? Oh. Excuse me. Oh, come on, man. I thought I muted the mic. Whoa. What? No. Don't do that. Sorry. Sneezed. This is one of the reasons why I take off the headset instead of hitting. There's like it's like a 3-button combination, and I miss it every now and then, and I'm just making a very loud noise into the microphone. I don't know of like a better way to do it though. I mean, I could just, because if I use any other combination, like I risk like accidentally turning off the mic when I'm using hotkeys. So it's kind of like a tricky thing, I guess. So we don't have R in this context. What does that mean? Oh, this is probably the one that's talking about here. Wrong number of arguments passed, flippable pieces. You need 2, right? RC and directions. Oh, That's kind of interesting. Actually, okay. Down. You want a list comprehension of this. You have possible positions, and you're going to say positions, position, possible positions, and then you're going to say direction over the directions. And you're going to have a sequence of directions, positions. So you're going to have position and the direction. There you go. Then you map cat this function over I guess you'd want to apply. I don't know if that works nicely. Could maybe make this a partial function or something, or even one of these. You could do this. That works too. None of our arguments pass to reverse C function. Where is that happening? Can we just do this first? Okay. So it's happening somewhere down the line here. All right. 0, 1, 0, 0, 0, 1, 0, 2, etc. What is going on here? Whoa. Hold on. What is this? Flippable pieces. Okay, let's just map. Don't cat, just map. What do we get? Okay. Few things to consider here. If it's inbound and there's an empty piece, but this is empty. Okay, so there's two things to filter on, I think. Two cases, if this is nil or this is empty, which there's a few of these cases. But it looks like we actually end up with, we don't need to concatenate these things, which is kind of interesting. The sequence ends up sort of working out nicely. So I take that back, I don't need to concatenate anything. We do need to filter on if I want to say or, right, either the first value is not nil or actually and it's got to be the first value is not nil and the second value is not empty. Kind of involved. Not really the most eloquent way to filter these things. I'll take it. All right, so 1 3 3 1 0 2 2 0. Okay, and now we update and let's see what we get. See how that works. See how that works. No arguments passed. Reverse C. Excuse me. So this ret of key value. What? How does this not work correctly? What do you mean? What do you mean? Excuse me. We're just gonna return ret and see what happens here. Excuse me. Okay. So there's something wrong with my update function here. Okay. Oh, no. Yeah, that's fine. Update. Whatever's going on here. So we're just going to update KV, right? Like that. Let's see what that looks like. Oh, I see the problem. We don't need. Yeah, I get it. We can just use this. We don't need this to be an anonymous function. There's nothing anonymous about this. This is quite literally get what's there or get an empty set and then push V into that, whatever is returned there, and update that. That's it. Yeah, okay, that makes sense. Right, that was why it's telling me the arity was not correct, because it didn't make any sense. Okay, but this doesn't make any sense though. What? This, huh? When we filter, we get, oh, yikes. Yeah, okay, my mistake. I understand. No, I don't understand. What? This is supposed to come from this sequence. What? Am I just going nuts here? Um, huh. Also, this doesn't need to be updated, it could just be associate. Oh, I'm the most confused here. Can we just print KB? Turn ret. What happens here if we do this? Okay. Okay, very interesting. So printing KV does what we were expecting. Right. Okay. Into empty set of V. Should have the same thing again. Nice. That's what I like to see. Well memed. Yeah, we get the same thing again. Oh, what is this? Whoa, 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 whoa. Whoa, 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 whoa. Oh. Red is just nil every time. Nice. We can do this. Throw this in here. Associate ret with K. Get ret default here into the, yeah. Okay. I don't know what we're gonna get with this. Okay. 1, 3, 1, 2. It is set. What the heck is this? What is going on here? I mean, what? Oh yeah, because this is a hash set now. Yeah, I mean, perfect. What is even going on anymore? I don't know. I don't know. Oh, okay, that works. I don't know what the deal was with the update. I don't know. I'm not gonna worry about it. But for some reason the associate works nicely. Oh, it's because update was supposed to take a function. That's why it was getting really confusing. Because it was, yeah, that is very confusing. Because update. Okay, now I understand. Yeah, update's supposed to take a function. That's just really threw me off. This is fine. Oh, everything's true. Nice. Okay. Yeah, that's more an issue of like, I guess I was just not too familiar with using update versus associate. So yeah, okay, so that's that. Done. Done. Now I betcha if I didn't reduce this way, I could have just pushed all of these into a hash map, but this actually handles multiple directions, which is kind of interesting. Which is something of kind of an edge case. Not really, but could be considered an edge case. Anyway, yes, this took a while. We got there. Took a while, but we got there. Let's see how we do. Nice, very good. And we can see solutions. I like this approach. It's not too bad, not too shabby. Obviously, much more concise approaches take about a third of the lines of code. Some of these. So more or less characters to use range here. Alright, so we got ways, next sequence, rest iterate, that other map, path, split with, sequence, O's into X, Y, X, Y, X, X, Y, when getting bored, let S be set of mapcat when I think I don't know what he did. I'm not really. I don't really want to go into too much detail, but there is such a thing as like using a more efficient or less efficient approach, and the less efficient approach might use fewer lines of code. I think that's what he did here. I think the approach I took is a little more efficient. I'm not entirely sure. Might not be, but I suspect that it is. Because you can often use like a more naive approach that uses less code, but it's just like way simpler to write, but is not more efficient at all. Yeah, I kind of don't care to look at everyone else's solutions. Although I'm grateful for them. Glad that they're there, but I'm not going to go into too much detail. Holy up, left, right, down. Come on, man. What? That's funny. Anyway, okay, fine. Yeah, I mean, there's probably some value in reading through the other solutions. Kind of don't want to, though. Excuse me. Tired. I am tired. Oh my goodness. n-1, n-2, n-3. It's pretty funny. E-board, C-board, and I-board. Hum. Ho hum. Hum diddle ha, hum diddle he. Shoop de whoop. Doobly bee. Doobly. Indubitably. This looks kind of like mine. Although, not sure what's going on here. Excuse me. Kind of looks like this was submitted on a different use case or something, and it was updated later. Condition P. What is that? Cond P in Clojure? I don't see that too often. Excuse me. Predicate expression clauses. Make sure you flush the buffer. Interesting. Yeah. I've actually run into that problem recently. I was working on a program. So you have a predicate and an expression. Takes a binary predicate, an expression, and a set of clauses. Each clause can take the form of either test expression, result expression, test expression, result function, ordinary keyword. Each clause, pred, test, expression is evaluated. If it returns logical true, the clause is a match. Binary clause matches, the result expression is returned. If a ternary clause matches, its result function, which must be a unary function, is called with the result of the predicate as its argument. So if a binary clause matches, then return the result expression. Test expression, result expression, predicate, test expression, expression. Oh, yeah, I mean, of course. Okay, test expression, predicate, test expression. So predicate, test expression, expression. So we say con if this one equals value, which is where's value? Oh, there we go. Let line be value. If one is equal to value, then you return this. That's extremely confusing, but that's pretty cool. That cond p. It's basically like a fancier switch statement. It's like a more specialized kind of generalizable switch statement. It's very neat. I think that's really cool. Yeah. Allegri, anybody? Cool. So you used cond p with their color and get in board position. It's equal to their color. You do something. It's equal to the empty set. Otherwise, does cond p have a default? Probably not. And actually, there's even a third. There's a third piece, which is this test expression with this result function. A little confused by this part. What's going on there? It's this value. Ternary clause matches its result function, which must be a unary function, is called with the result of the predicate as its argument, the result of that call being the return value of cond p. Single default expression can follow the clauses and its value will be returned if no clause matches. If no default expression is provided and no clause matches, the illegal argument exception is thrown. All right, I don't fully understand what's going on here. It feels like there's just a lot happening out in one spot. What is there an example of this? Text expression, result expression. Oh, there we go. Okay. Yes. So you literally just put this keyword in there, and then say, okay, if it's like 1, 2, 3, 4, then this decrement is called with 4. Oh, and so it returns 3. Amazing. That's a unary function. So if it was like 3 that matched, you would get 6. Oh, okay. That makes a little more sense. Yeah, examples make a big difference in terms of understanding. Big difference. All right. I don't fully. Yeah, I don't know. I mean, I kind of don't want to like take the time to figure out what these folks did. Interesting though, almost all of these used fewer lines than I did. I used almost 30 lines total, almost 30. 15, 25, 23, 25, 15, 24, 26, yeah, 30. Yeah, I'm like one of these guys. Excuse me. Excuse me. Excuse me. Yeah, okay. Anyway. Alright. Yeah, I mean, I think they're all probably similar to each other and what they do, the approach. There may be some value in coming back to this, but I just don't want to. Just don't want to, you know. Just don't want to. Yeah, there's a lot going on here. Kind of interesting, but I think he did something similar to what I did, except there's a couple things that are different. I'm not totally sure. I think one of the things is that he combined a lot of stuff, so it just kind of goes one into the next. It looks like, which is fine. It's all well and good, but it's not the most readable thing, you know. It's kind of can take some time to parse, to understand. It's okay, I guess. May not be too judgmental. I'm not totally sure. Maybe a little too terse. These two, possibly, quite possibly. Terse is generally good, but it might be a little too terse. All right, Gus's conundrum. Hard. Okay, logic, fun, brain teaser. Create a function of no arguments, which returns a string that is an exact copy of the function itself. Read this if you get stuck. This question's harder than it first appears. It's worth the effort to solve it independently if you can. Gus is the name of the Foreclosure Dragon. Oh man. Oh. That's penis.gif. Come on, man. Trying to just look at pictures on the internet and just end up with penises. This is ridiculous. The Foreclosure Dragon. I guess that one is the name of it. It's Gus. Okay. Create a function of no arguments which returns a string that is an exact copy of the function itself. Ah. This is interesting. It's harder than it looks. This is one of those this is one of those lambda calculus shenanigans. Oh boy. So if you quote it, turn into a string, it's equal to itself. Oh, quinundrum, a quinoxical, yeah, a quinine, quinon, a quinon. Yeah, quinon. Hold on, it's not my coin on. Program that returns itself. A quine. There we go. Quinundrum. Quine. Quine pronunciation. Come on, there's no quine. I don't know. Okay, fine. Quine. So we want a quine. Okay, that's fine. We can get ourselves a quine. How to do though? How do we get ourselves a quine? Quine. We want to return itself. So this is kind of interesting. What we can do is get a function. Returns. It takes a function, right? And what we can do is say the string of itself as a string. Maybe we can, what do we get quine? What does this look like? Or f. I would call itself. So if we used quine of quine, and we want quote, I guess, and then as a string, something like this. Does that work? I don't think so. Oh, interesting. Something like this is what we're after. F. All right. No. Like, okay, let's do this. Turns a string of itself. So like a function that returns a string would be something like this, right? So if we print line of f, we get a string. Oh, yeah. Okay, that's fine. Now, how can we convert this to a string? All right, this function. So if I took print line of f and quoted it, like, or print line of f as a string, like how do I ever, if you quote the function, the string of the function, you quote the function, right? Like, what do we get? Interesting. So yeah, this is definitely a like lambda calculus thing. if you take the string of f, what does this do? It's f and string of f. What do we get? Okay. So this, now, if this is an anonymous function, right? Some kind of anonymous function that says function check. Yeah, this is a, what do they call that? It's a higher order function that we need. Okay, it seems that this is what we want. If we quote this function, so give it this anonymous function. All right, let's call it like, yeah, you gotta, okay, I think you gotta do this with an anonymous function explicitly. So let's try it, see how far we get. We're gonna say string of this function, and then it's gonna be equal to calling that function, right? Oh, wow. Okay, I think I know what to do. Oh man, this is interesting. You definitely want to do something where the function takes a function, right? So we'll call it function f, and we'll take a function g, right? And well, you call it without any arguments, though. Oh, what? Oh no. Okay. Well, there's f. And the thing is, what this would need to return is if it returns a string literal, then it would need to return whatever it is, the recursive thing. Oh man, what about nil? That's not really a function, is it? That doesn't, no, there's no way. Come on. That doesn't make sense. Oh. A string of nil, and then also nil. No. Can't call nil, okay. Ah. I want to say you got to use a function f. Alright, let's try again. It's definitely a brain teaser. It's quite the brain teaser. You gotta use some function f that takes g, and then you've got to partial this thing with itself. So you end up with like function f which takes g. You really, no, you have some function, right? Call it x. It doesn't take anything. And then you have this let in here, which has an f. Call it some other function f, which does take a g. It's about to get involved, man. So we've got this x out here that we're going to eventually get to, but there's no way this makes any sense. Basically, I want to take the function, this function, and convert it to a string. I can maybe, I want to take a form. How do I evaluate a form? If G is a form, right, if you take some form, I want to say something like form, and then if you evaluate that form, right, that returns if you get some function that has takes a form, and you evaluate that form, right? Get some f, some form, you evaluate this form, and the form is this thing quoted, right? This function quoted. How do you give itself give the function to itself? And how do you get the quoted form of quoted version of a form? I want evaluation, and I want quote. Now this is going to be interesting. It yields the unevaluated form. A quote, print line, version, quote 1. How do you get the unevaluated form of a function? Eval load string resolved. Evaluates the form data structure, not text. Returns the result. How do I go from function to a form? And we can var x. If we var f, what does this do? One, two, three, four, five. There's got to be some fancy footwork we do with passing functions. This is a higher orders function thing, absolutely. But I don't know why or how or what. Something I'm missing. So this gives you the variable. What I want to do is, I don't want to invoke it. I want to, or recur on it. I want to, don't want to destructure. How do you do this? Macros, evaluation. How do I, quoted form of a function, Clojure. How do I do this? Quoting without confusion. You know what? We don't necessarily need, like, I understand the quoting of the anonymous function works. But the thing that's weird is if you call this function and return something, right? The returned value has to be whatever characters you're going to get if you quote this function. So you got to return some number of characters. We'll call it, let's say it's k characters, right? So you return these k characters from this result. Taking this quoted form and taking the string of it, you've got to return exactly the same characters that calling it. Excuse me, what for this? But here's the tricky part. If there are k characters that must be returned by quoting this function, meaning there are k characters that comprise of the entire function, then those are exactly the same characters that must be returned by the function. So I think what you end up with is you've got like a kind of iterator type of thing where you would say you've got to have a function that is somewhat compact that will return each of the pieces in a kind of sequential way. Like even if you have two characters, just fn, right? If this returns two characters, fn. If this requires, it's going to require at least these characters, right? So your function could return that. But the problem with returning that is then your function then needs to return this entire thing. Right? Now, suppose your function needs to have at least this much. Now your function needs to have at least this much. Yeah, if your string is going to return this, if your function is going to return at least this much, then we can get rid of this white space, or some of it. Now your function needs to be this. And so what you end up with is then you've got to say, well, your function also then needs to be this is a string. Which is this, it looks like. Yeah. Or we'll say this. Right. And you say, well, then your function needs to return, first if your function needs to return at least this, then your function's got to return at least this, which is this one. And then your function's got to return this, which looks like this. And so you end up with a situation that repeats infinitely, right? You end up with something of an issue, something of a problem. Unless, of course, you return the function that is itself the function that returns itself as a string, i.e. the self-replicating function. Now the self-replicating function looks like this. It's f of, it takes two functions, f of f and f, and it gives you f of f. Yeah, something like this. F is xx, and you're going to have x of x, or rather f of f. I don't know. It takes itself as a function, and it just calls x of f. Something like this. I don't know. I don't know what the self-replicating function would look like in Clojure. I think it's this. Yeah, I take it back. The self-replicating function is a function takes x and it computes x of x. That's the self-replicating function, right? And so what you would do, I think, then is call f of f on itself with itself. All right, so you declare this and you say f of f. Oh boy. Interesting. You could even say like partial f of f. Excuse me. Now it's bound to itself. And will call itself on itself. Right? And what if you did this? What if you did this? Make it anonymous. Excuse me. This is starting to look like Turing's combinatorial. That's what it is. It's combinatory rather than combinatorial. Yeah, this is starting to look like a combinatory operator. Because they're just combinations of functions. Yeah, combinatory operator it's starting to look like. Look at this, man. This is crazy. This is crazy. Whew, excuse me. Yeah. That's pretty wild. Function that returns itself. It's more or less an anonymous function. Or returns itself as a string. Yeah, returns the code required. Yeah, returns its own function, its own thing as a. Excuse me. Excuse me. So you need something like this. Self-replicator, and then you gotta call this partial function. How about this? It'll actually return a partial function of x with itself. And this is the function. So if you call it, it'll actually just call this function. Which is then, I want to say, like, if you pass a function, you can get the quoted function. What the form is. Something like that. Like, how do you... That's pretty much what we need to do, is we need to, like, abstract away something here. Like, how do you... Like, I can do some manipulation, some higher order functional manipulation in order to get a function into our function, and then you can use that function, which would be itself. But then we need to actually convert it to a string. Is there a way to do that? Function to string in Clojure? Senior software developer, Clojure Java. Cool, Clojure Agile. All grades. CQ5. SAP. Audible. Newark. Functions defined with the define form. User map meta name. Defn nothing, user nothing, meta sum nothing. As far as actually the var rather than just the function value the var holds. Reader macros. Demunge. This is the function name, but we're looking for, we want the function form, you know? There's a way to do this. It's like expansion in Clojure. Like we want to macro expand form. No, that doesn't really do it for us. Can we do this string to a function at least? Because maybe we can do it that way. Let's see. Might need a cheat sheet as well. Huh, big data developers. Interesting. Resolve. Oh. Maybe that's what we need to use. Alright, I think we can do is pass a string that we resolve, right? So we'll say the function is a string, right? What I want to do is say, okay, let's get some function. That's going to take a string. And the string is going to be itself, right? And we're going to resolve the string, which is itself. which then gives us a function which is itself. And okay. And eventually we want to print S. Okay, so we want to, I don't know, we want to return S. So this returns itself S, this function. And now what we want to do is we want to partial this function with itself. And if we call this function, if we return the quote, if we call this, we're going to get I want to bind this string. We bind this string to this function, then we're going to resolve this S, which is this function with S, and then return S, which says resolve S, which resolves S, which resolves S. I think this just gives us an infinite loop. Quite possibly gives us an infinite loop. Maybe we want to actually not just give it S, but give it, yeah, what is it? There's some, it's a function X which calls X on X, right? And we want to say something like there's S, and you've got to resolve S, which does what? Gives you the function. And then we want to call this. We actually want to call it here. Okay, so you have X calls X as an argument, right? I want to say you want to resolve S and then resolve S as an argument. Something like this. And what that'll do is it'll take some string and I'll say resolve that string into a function and then call with an argument this resolved function, right? So this function will call itself, basically. Well, yeah, this function will call itself. Okay, interesting. Now, if you give as a string this thing, right, to this function, and you call partial. If we do that, you've got the self-replicating function now, which is resolve of s on resolve of s, which I want to say I probably want the Turing combinator in string form, because what it returns Are we back? Okay. Well, this is kind of interesting. My charger is so poor that it's actually just not charging my phone. Turns out I don't need a new phone, I just need a new charger, because I have a much higher quality charger that I use in my vehicle, my car, and it works a lot better than this one does. So this is just like a cheap charger. It doesn't work very well. I need to get myself a better charger. Also, it didn't this only dropped for a moment, my connection. Anyway, so there's like lambda calculus we could look at. Turing. Okay, so this is interesting. Turing's fixed point combinator, for every lambda term x, this reduces to x of x, which one can confirm by hand. Curry's paradoxical y combinator does not have this property. So basically, the Turing combinator of x reduces to x of the Turing combinator of x. Reduces to f of itself, or x of itself, which is a little bit different than what the y combinator does. It just means that they reduce to some common form, common term, x applied to y of x. The reason why I want to use I was thinking about using the Curry combinator, f of x, which is the self-application combinator, f of x. The reason for this I get really confused how we know these things come to a common term, whereas these don't come. This actually isn't just a common term, it's actually reduces to itself, which confirmed by hand. So I want to say if you use the Turing combinator, you can bind to it and call, or just call it on itself, not on itself, but on using a Turing combinator with, oh boy, using a Turing combinator with, I want to say using resolve, and then also with a string, which is itself. It's confusing as all heck. Basically, you need to use a combinator ultimately. Yeah, you need to return a string that returns. Yeah, okay, so return a string that when resolved is a function that returns a function that returns a string. So you want to return a string that when you resolve that string, it's a function that is itself. That when you resolve this string, you end up calling a function, or you end up with a function that will return a string. Oh man, it's like hard to express this. I want to say if you could express it in English, then you could express it in a combinatory construction, I guess, or combinatory function. So it's going to return a string, and that string, you're going to resolve that string. If you were to resolve that string, right? So let's say if you were to resolve that string, you would get another function which returns the same string, which is the function that when resolved returns a string. That is the function that if resolved return a string. If not resolved, what does it do? Doesn't return anything, I guess. Is there a resolved property? I wonder. Holy guacamole, man, I don't know. I don't know how to do this. We're looking for a quine. This is hard, man. Also, I'm going to bed soon. I'll probably end this here, go to bed, come back to it tomorrow. If you were to call this, all right, I wonder what happens if you call these things. I think you get lots of like infinite loops. What does this do? I'm curious. doesn't work. It just says no. What if you bind, you say result, let's just say this is like some function. It just says x, and we just return x. What does this do? Hold on, is that right? There's this function, it's a partial, it's function s, which resolves s and returns s. What happens when you resolve this function x of x? And you give it this s. Just returns s, which is this function. Partial. Class cast exception. String cannot be cast to class. Symbol. Really? Do we quote this maybe? I don't know. List. Do we just symbol this? I don't know. Very confused here. I don't know, no idea. I really don't know. I guess this resolve doesn't quite work as I thought either. How, string to function Clojure. Converting a string to a function. Resolve symbol. Resolve symbol. What does this do? Time for bed. Time for bed. Alright, what do we get here? What happens? Also jobs, man, jobs. Who doesn't love jobs? Front-end developer. It works. Whoa, check me out. Cool, yo. Cool, man. I shouldn't say cool, yo. That's no bueno. No bueno. No mas. No thank you. No thank you. Nil. What was that? It's definitely time for bed. If I do this, can I call this function? This actually doesn't work. Syntax error, null pointer exception. So okay, I think the problem is that this doesn't do what I think it does at all. Yeah. No, I was kind of hoping to like use a string. Can load string, read string. I want to say eval, maybe it can work. Excuse me. Read string. We can eval read string. Okay. So that works. So eval read string is what we want. Now, this is going to be interesting. Wrong number of arguments. All right, awesome. That's what we want. Okay, so we want to eval read string. All right, this is good. This is progress. So eval read string of a function which takes x. All right. Now what I want to do is partial this thing with this guy. And I'm curious now, first if this compiles and runs, then I want to say, let's actually execute this thing. Print line. And finally, just execute it. It does execute. That's crazy. And what? Cool. And what happens if we? This is dangerous, man. Using eval. Wow, look at that. Holy smokes. So we can actually bind this thing and call it. Now what if we don't partial this? Amazing. That's fun. I need to go to bed now, but I think this is maybe fodder for tomorrow. We can think about how to solve this. So we'll end it there. We've got another, how many problems left? This has definitely been really challenging. I'm glad we tried this series of problems here. We got another, was it 56 we gotta go to? It's got 31 more problems. Once we solve this, we'll be at 30 problems. We're making headway. We're making headway. I want to try to finish this by the end of the month. It's another week, so we can finish, how many, 7, 8 days. 30 problems in 8 days. It's like 4 problems a day. Should be able to do 4 problems per day. Tomorrow and the day after, we should get some time to put in, like, get a whole boatload of these problems done. So yeah, I'll end it there. Thank you for watching. I will talk to you all soon. Have a good rest of your night. Take care. Take care.